So we talked about batteries and use of batteries and discussed that batteries are not the same. In a battery, redox reaction takes place. Battery is a place where electrons are transferred. Reduction takes place at the cathode, and anode oxidation takes place. Reduction is gain of electrons. Copper 2 plus going to copper is gain of electron, therefore reduction. Zinc going to zinc 2 plus is oxidation. We talked about that. There are many redox reactions that take place if you didn't isolate the two electrodes. For example, Statue of Liberty turns green because copper with oxygen in the air produce copper oxide. Normally, unless we make a electrochemical cell or galvanic cell, the electrons cannot be used. They are transferred directly. There are half reactions for zinc copper reaction that we discussed in the previous slide. So 2 electrons are transferred from the oxidation half reaction to reduction half reaction. Oxidation half reaction takes place at anode. Reduction reaction takes place at cathode. Half reaction, we practice half reaction. First one is a oxidation reduction half reaction. Second one, B, is a reduction half reaction, oxidation half reaction. Second, B, is a oxidation half reaction. Third one, C, is a reduction, and D is a oxidation. E is a reduction, gain of electron. If electron found on the reactant side, that's a reduction. Electron found on the left side, on the right side, product side, oxidation. So we remember that idea. Oxidation is loss, oil rig. Oxidation is loss, OIL. Reduction is the gain. Reduction is a gain of electron. There are also another mnemonics. Loss of electron is oxidation. Gain of electron is reduction. We normally call Leo. There was a lion in one of the Disney movies, Leo. Leo, the lion, says G. Leo is the loss of electron, or is oxidation. Gain of electron is reduction. You have to remember these two. Well, what is reduction and what is oxidation? When you connect a battery to a circuit and have a switch and a bulb, as in the figure in here, electrons flow from negative electrode, that is anode, to the positive electrode, which is the cathode. That's how we say electron flow opposite to the current. Normally in a battery, positive end and the negative end, we consider positive electron flow. The current flow is from cathode to anode, but electron flow is opposite. The transfer electrons through an external circuit produce electricity. The flow of electrons from one region to the another is shown by difference in potential. Depending on the redox reaction used for the battery, the voltage is based on redox reaction. Different redox reactions have different voltage. That's the driving force for electrons. To enable this transfer, electrode are placed in a cell as site of chemical reaction. So normally you separate the two electrodes, reduction F reaction cathode and the anode, with a thin membrane or salt bridge in the one we're going to discuss later. So you produce electrochemical cell, galvanic cell. The difference in electrochemical potential between two electrons is the voltage, is expressed in voltage. You understand, when you have a battery, you measure in volts. Ohm's law is a expression where V is equal to IR. The current flow through a wire with resistance R is related to voltage between the two ends of wire. V is the electrode potential, cell potential, electrochemical cell potential. I is the current that flows through the wire. R is the resistance. The red guy in there controls that's the resistance. Higher the resistance, it's difficult to flow electrons. So therefore, less current for given chemical cell. So that's called the Ohm's law. Different oxidation states are used in electrochemicals, galvanic cells. The oxidation states are given in the form of periodic table. Here we have gone over some of that. Group 1A is positive 1, sodium, potassium, lithium. Calcium is 2+, magnesium is 2+, and the transition metals have a variable oxidation state, different oxidation state, more than one. Charge species oxidation state is charge on the ion. If a metal is not charged, oxidation is equal to 0. Metallic forms are oxidation, there's no charge, therefore oxidation is 0. There are various charges present in different metals and anions and cations. You can find the oxidation state for different things using the periodic table. Electron transfer take place within its electrode. Electrical conductors that serves as site of chemical reaction. Anode is where oxidation is taking place. We talk about that. Cathode is where the reduction takes place. Depending on their group, elements have different oxidation state. For example, zinc has only one oxidation state. If you check on the zinc is in the group 12. Zinc have only positive 2. So therefore, copper has 2 oxidation states, copper 1 and 2. But normally, copper oxidation takes place from copper to +2. Galvanic cells are batteries that are made from different redox reactions. You can pick up a redox pair, half reactions, and produce many kind of electrochemical cells. A battery is a system for the direct conversion of chemical energy to electrical energy. Batteries are found everywhere in today's society because they are convenient and transportable source of stored energy. If you have a camera, you cannot, on the road, you can take a picture since you have the batteries. Even if your car, stop somewhere in the middle of the road, you can crank it up because of the lead acid batteries. Batteries are shown here are more correctly called galvanic cell. It's another name for batteries, galvanic cells. Series of galvanic cells that are wired together constitute a true battery, like the one in your car. Some batteries are several batteries connected. Car has 6 batteries of lead acid batteries, 2.0 volts each. 6 times 2 voltage is 12. Some of you may have come to know that car battery voltage is 12 volts. So if you have a problem with the battery, you first check the voltage of the battery. Now, in the laboratory, galvanic cell model is copper and zinc cell. Normally, this cell is shown on the left is the anode. On the right, copper is the cathode. So it explains how electrons are transferred from electrode. Zinc dissolves into the solution. If you look at the zinc anode, it is kind of getting smaller. And the copper solution, copper ions are deposited on the copper electrode. Therefore, zinc dissolves, copper is deposited. Therefore, as the chemical reaction goes on, zinc is turned into zinc 2+. Copper 2+ is turned into copper 2+, copper metal. So we can write down replace these 2 compartments with different half reactions, like zinc going into zinc 2+ plus 2 electron oxidation take place in zinc. Could be replaced with many electrodes. So is the copper. So you can pick up your own cell. Most of the cells that we use are produced, galvanic cells are produced based on the practicality and the voltage. So let's look at the common galvanic cells. Nickel cadmium, which is rechargeable. The nickel cadmium system has voltage of 1.25. You can write down a nickel and cadmium cell like the copper zinc cell and create a one. So nickel and metal hydride are replacement for nickel cadmium that are used in consumer devices and hybrid vehicles. Nickel metal hydride is the one that used in the hybrid cars initially. Alkaline batteries are famous. They have 1.5. They have manganese dioxide and zinc. We're going to look into that. Lithium batteries are the small cells which are not rechargeable. Some of these cells are rechargeable, some are non-rechargeable. Alkaline is not rechargeable. Nickel cadmium is, yes. Nickel metal hydride also could be recharged. Lead acid batteries, automobile batteries could be recharged. A battery is 2.1. Car battery has 6 cells of lead acid battery connected in series to produce 12 volts. Lithium ion polymer batteries, 3.6. So this is rechargeable. The first run lithium primary batteries are not rechargeable. Lithium ion polymer batteries are rechargeable. That's mostly used in computers, cell phones, portable electronic devices, and power tools. If you have a power tool, there's a battery, rechargeable battery, that is lithium ion. Lithium ion is the most common battery, rechargeable battery that are used in Tesla models, and it's very popular now. The voltage of a battery is dependent on the chemical composition, whether it's copper and zinc electrodes produced in the battery or other nickel cadmium or etc. So, but batteries size also indicate the capacity of the battery. Larger batteries have more chemicals in it. They can sustain the flow of electrons longer since they contain more material. For example, AA, AAA battery is smaller than larger D size batteries. Produce same voltage, but larger cells have greater capacity. Primary batteries are called non-rechargeable. Secondary batteries are rechargeable. Let me see whether if I missed anything. This is the alkaline battery. Manganese dioxide, I gone over this previous class. I don't want to spend all my time in here today. The cathode reaction is zinc. Anode reaction is zinc, outer layer of zinc dissolves. That's the half reaction for anode. Cathode is the manganese dioxide. Carbon is just a conductor in the middle, carbon. So it's a cathode. Manganese dioxide is cathode. Manganese dioxide, manganese 2 oxide, manganese 4 oxide turn into manganese 3 oxide. So it is a reduction. So overall reaction is this. This cannot be rechargeable. This is not rechargeable. Like in many chemical reactions, which are reversible, not many chemical reactions are reversible. Batteries also have the same feature. Some of them are rechargeable, reverse reaction can take place. They are rechargeable. Nickel cadmium is the secondary rechargeable battery that we use in household appliance electronic devices. So I have a set of rechargeable batteries in my home. The highest reaction is cadmium and nickel oxide. So there's a recharging or reaction is reversed. While recharging, it acts as an electrolytic cell. While charging, it's a galvanic cell. For charging, above reaction proceed in the opposite direction. Lead storage battery. There are 6 batteries here if you counted the green plates and brown plates. Anode is a cathode is a lead, where lead is turned into lead 2+. Anode is a lead, turned into lead 2+, plus 2 electrons. Cathode is the lead oxide, lead 4 oxide. That turns into lead 2+, 2 plus. That's the reduction. So cathode is lead oxide and anode is lead. So this is the reaction that takes place with sulfuric acid. So that's car batteries are corrosive. Therefore, you have to be careful when you handle them. There's acid in it. Okay, now I'm going to start a new material from you. The batteries that we find, lead acid, nickel cadmium batteries, nickel metal hydride batteries, lithium ion batteries, polymeric form, and ion batteries, all in the top right corner. If you look at this, there are two axes. Energy density per weight is on the vertical axis, y-axis. X-axis is per liter energy density. The lead acid batteries have the lowest energy density, volumetric energy density, volume-wise, lowest, also weight-wise is the lowest. So that's the lowest energy density. So the car battery cannot be used as a battery to run vehicles. So the nickel cadmium batteries have low energy density. So volume-wise and the weight-wise. Gravimetric is weight, volumetric is volume. But the best batteries are for energy densities on the upper left, right, top, upper right, top right, are lithium polymer batteries. These are the main ones that are used in Tesla and other devices, power tools. The nickel metal hydride are used in Prius, but it is not that, it doesn't have high energy density. So it is good in hybrid cars, but electrical vehicles cannot be made from nickel metal hydride batteries. Electrical vehicles are one that are not hybrid. They are just electrical vehicles use only battery power. So you have to know about the energy densities. Lithium ion batteries has the highest energy density. So stored in the electrode and weight of the volumetric volume of the battery, that's related to weight and the volume of the battery, energy density. How does a lithium ion battery work? One of the most used batteries is the lithium ion battery. Lithium ion batteries have lithium ions. On the cathode, made out of cobalt oxide plus lithium. And the anode is made out of carbon graphite layers here. The lithium ion, while discharging, moves from carbon electrode to metal oxide. And charging, lithium ion moves back to carbon electrode. So during the discharge, lithium ions in the carbide, C6, move through the electrolyte. Electrolyte is the one separating the two electrodes and pass into metal oxide. Cathode is a lithium combining with metal oxide, cobalt chloride, cobalt oxide. Lithium metal oxide is lithium cobalt oxide. So that way, lithium ions are passing through discharging, charging cycles. So lithium ions are reactive. So we have to be careful about lithium ion batteries. They can cause fires. Initially, there were explosions because of the reactivity of lithium or some sodium batteries with higher reactivity towards water, oxygen, and nitrogen. So non-electrolyte must be, non-aqueous electrolyte must be used in lithium-ion batteries. The electrolytes are not aqueous solutions like in other batteries, alkaline batteries. They are non-aqueous solution. Otherwise, lithium can react with the water and explode. So, and the battery packs must be sealed to prevent exposure to air. So air also a possible factor that lithium can react with air and ignite the battery. Fires are initiated if the separator between electrode compartment is broken, which short circuit the major heat and produce major heat. Also, circuitry to prevent overcharging may be faulty. When overcharging takes place, the lithium cells get heated up, then they can explode. So faulty overcharging circuit or broken seals could cause the explosion in batteries. Now I'm going to change the topic a little bit. Now, this is a big deal in energy storage. The electrons are stored in electronic circuitry in capacitors. There are two types of capacitors. One is regular capacitors, small ones, two electrodes, positive and negative, separated by dielectric material with a distance of d. And the supercapacitor is the one similar to capacitor, but they have electrolytes between the capacitors. They have small distance. The distance is, electrode distance is between the cathode and the negative layer that appears, a double layer. That is the distance between, small distance between those two first layers, positive and negative. These are charged particles. On the other hand, battery is a electron source based on chemical reaction, electroactive material, or that can undergo redox reaction. So you can use one of these to produce electricity. In circuits, smaller circuits, capacitors do that function. They don't need to provide too much of energy, low energy. They are low energy, higher life cycle. So they can be recharged many times very quickly. But supercapacitors also high cycle, moderate energy. So they have more energy than more electrons. Electrons are transferable than regular capacitors. So on the other hand, batteries are slow to produce charging, low cycle life. There are not many cycles compared to high cycle life for capacitors. Therefore, capacitors are much more durable. So now there's a lot of stuff going on. Battery should be replaced by, could be supplemented by hybrid forms of attachments like capacitors, capacitors and battery. So supercapacitors are replacing lead acid batteries now. So you're going to hear this in the future. Supercapacitors are the ones that provide fast source of electrons, current, and they could be used in many applications. So let's compare the supercapacitors versus batteries, their performance. Lithium ion is the one that is popular, so we compare it to supercapacitors. Charging time to charge a capacitor to full, only 1 to 10 seconds. Lithium ion takes about 10 to 60 minutes. There's a lag. So cycle is for capacitors is about 1 million, but lithium ion is lower. Cell voltage, it depends on the material, capacitor material. Lithium ion is 3.6 to 3.7. Specific energy per gravimetric energy. Lithium ion has much more power because of the chemical reaction, has a lot of chemicals in it. Therefore, it has a lot more energy density. So specific power. The power-wise, supercapacitor has more power available, but low density. Cost is much higher for supercapacitors, but large for lithium ion is much smaller right now. But as the applications comes out, the supercapacitor is going to be cheaper. Service life of supercapacitors is 10 to 15 years, whereas lithium ions is only 5 to 10 years. So therefore, there's an advantage using supercapacitors along with lithium ion batteries to reduce the service life of increase the service life, decrease the cycle life for lithium. The temperature wise also, supercapacitors is a much higher range than lithium ion batteries. So these are the considerations that you should take into account when you're considering using supercapacitors and batteries in different applications. Energy densities is like analogy was energy power densities is a water bottle. Size of the water bottle, just like in a lithium ion battery, they have a lot more power. But size of the opening is smaller. You cannot draw out because draw out lithium ion battery power takes long time. But for supercapacitors, size of the bottle is smaller, but size of the opening is large, therefore quick availability. If you look at this diagram, so if you look at the range, specific power, and what is the specific, I cannot see it. Specific energy, specific power. The supercapacitors are good with the specific power. Supercapacitors are also good in that sense. But capacitors have lower energy, so therefore we cannot use them. Supercapacitors have in-between energy. But the energy-wise, energy density-wise, batteries have more energy. Now we're going to talk about fuel cells that are coming in to replace the batteries, nickel-cadmium batteries or lithium-ion batteries. So out of these three alternatives for energy storage, the fuel cells are the best. Batteries are next, but they have very slow release of energy. Supercapacitors and capacitors have much higher specific power. Energy density wise, much more energy in fuel cells and batteries. So this is a kind of a comparison of two possibilities, batteries and supercapacitors. And the fuel cells we're going to talk about in a minute. I'm stuck here. To storage batteries in the hybrid electric vehicle, plug-in hybrid vehicles, electric vehicles. We're going to talk about this. Combined use of gasoline and battery technologies is the hybrid electric vehicle use. So I had a Honda Insight, but it has a system that when your batteries are low, the gasoline is used more. When you use the gasoline, battery get recharged. Then it shift back between two alternatives, gasoline and battery technologies. So it will cut down the gas mileage. It will increase the gas mileage. So you can, hybrid vehicles have higher miles per gallon. Many hybrids, unlike conventional gasoline-powered cars, deliver better mileage in city driving than highway speed. One of them is because highway speeds, to get the speeds up, you have to have a lot of power. So therefore, more gasoline is used than the battery power. Therefore, small, slower speed driving, low speed driving in the city is better with the hybrid car. The average gasoline powered vehicles emit 6 to 9 tons of carbon dioxide. If you increase the mileage per gallon by 5 miles, fuel efficiency can reduce 18 tons over vehicle lifetime. So therefore, these have an effect on carbon emission. Use of hybrid vehicles are a good thing. Now, fuel economy, we're going to compare some of the models. These are electric cars. Did I miss something in the? Okay, I'm going back. Okay, we first going to talk about electric vehicles. Electric vehicles are run mainly by batteries. So they equivalent to gasoline powered cars. So they produce 150 in the city and the 122 Hyundai Ioniq. Then Tesla produce 140 miles in city and 124 on highway. So there are several other cars, Chevy Bolt, 128, 110, Volkswagen. These are totally electric cars, all right? So we're going to, the Tesla is one of the most popular right now. It's an electric vehicle, not a hybrid car. So let's look at, we are comparing plug-in electric vehicles now. First came the hybrid, then came the electric, then combined together electric vehicle and hybrid vehicles. So plug-in electric vehicles. Plug-in means electrical vehicle can be plug-in also. Hybrid means gasoline also. Plug-in electrical vehicles have much higher mileage than the electrical vehicles, than the hybrid vehicles. I'm sorry, than the hybrid vehicle. Electrical vehicle still has the higher mileage. So plug-in is still using gasoline, some. So plug-in hybrid electric vehicles. We have hybrid vehicles, electrical vehicles, plug-in electrical vehicle. There's a combination of both in the last one, public plug-in hybrid electrical vehicles. So this should have been the first slide. This is the hybrid electric vehicles. We talk about electrical vehicles. Then we should have talked about plug-in hybrid electrical vehicles. Hybrid vehicles have lower mileage compared to other two, okay? So they use battery and gasoline. Worldwide electric vehicle subsidies. If you look at subsidies, there are many countries that subsidize use of electrical vehicles worldwide. So I cannot read this, it's too small, but if you look at this, US, there is a federal tax credit for up to $7,500 toward the purchase of a new plug-in hybrid. All electrical vehicles have been offered since 2011. Other policies and incentives have been developed across the world to promote charging infrastructure development in major cities. Charging infrastructure development. So if you can read this map, you can understand how different countries. We are a little far behind than other countries giving incentive to electrical vehicles. So, but we will be catching up soon. So when you look at the electric vehicles, which use mainly lithium-ion batteries. That China is the car sales wise, China is leading. Europe is the second. United States is the third. So if you look at electric car sales, sales are low in the China, but the United States and Europe are in the middle. But other countries, for example, this Japan is much higher sales. Like United Kingdom also, in the France, Germany is also in between. Okay, Norway is little, there's a upward shift in these countries. In United States, it's going down. So you can see how people around the world are using electrical vehicles sales. Tesla is one of the most popular electrical vehicles using lithium-ion batteries. So there's a talk about using other battery systems to give more power and run more distances. The most significant increase in plug-in hybrid electric sales worldwide were in Norway, Germany, and United Kingdom. So plug-in hybrid electrical vehicles are in Norway, Germany, and United Kingdom. So we are kind of behind. Now, let me talk about another development that's taking place in the world. There's a cell called fuel cell. It's a galvanic cell that converts chemical energy directly into electricity without burning the fuel. Normally, if you burn hydrogen, you have to have oxygen and burn it and get the energy, heat, then run turbine and produce electricity, etc., like in power plant. But in fuel cells, two electrodes are made out of electrode reaction, hydrogen and oxygen, separated in two compartments like copper and zinc. So there's a anode and cathode. Anode is hydrogen half of the reaction. Cathode is oxygen half of the reaction. The fuel is hydrogen. Oxidizer is oxygen. Flow into cell to continue chemical reaction. Unlike in a battery, where the chemicals are limited by the makeup of the battery, this is continuously replenishing the chemicals, just like you burn gasoline in the car continuously. They are passing through the hydrogen and oxygen, passing through fuel cell, produce energy. So they have the highest energy density. So therefore, fuel cells could work better than conventional batteries. How does the fuel cell work? The fuel cells need hydrogen. You follow this line, hydrogen tank. Let me see where the hydrogen tank is. Hydrogen tank is on the top right corner. So one is hydrogen tank. That is the tank here. The hydrogen is stored in this tank. Fuel cell is in the middle. So these lines should be in the middle, the dark place. In the middle here, fuel cells. And the hydrogen tank is on the back. So a motor is on the lithium. They also have a lithium ion battery to store energy because just like hydrogen burning is a slow process, even though high density, you have to run a car, you have to have faster space. Therefore, it's a kind of fuel cells with the two cells. One is nickel lithium ion battery and the fuel cell battery. So this is, the hydrogen tanks are pressurized up to 5,000 pounds per square inch. So there are gas stations that contains hydrogen pumps. So that's a lot of them are in California. So this is, pressure is very high in the hydrogen tank. Precautions has to be taken to prevent explosion. So this is the half reaction for fuel cells. Anode reaction is hydrogen. Hydrogen release electron, producing hydrogen plus. Cathode reaction is oxygen going into water with the hydrogen producing the anode reaction. So overall reaction is hydrogen plus oxygen going to water. This is pollution free. There's no carbon dioxide involved. Therefore, fuel cells are the future batteries with high charge density, power density. Combustion versus fuel cells. Combustion versus fuel cell technology. We are going to compare regular cars with the hydrogen fuel cell cars. Combustion, hydrocarbons, alcohols, hydrogen, wood. Hydrogen also could be combusted. That produce oxygen from air. Then products are water, carbon dioxide, and carbon monoxide. That's the conventional pollutant, more carbon into the air. Other consideration, rapid process, flame present, low efficiency, useful for producing heat. It is faster process because the flame is present. However, it is low efficiency. Not all the energy is converted into useful energy. Heat is dissipated. On the other hand, hydrogen fuel cell, hydrogen from the tank, oxygen from the air, that's free. Produce water and electricity and heat. So process, no flame, quiet, efficient, useful for generating electricity. It's only a slow process. Therefore, you have to supplement it with nickel cadmium battery, lithium ion battery to store some energy to sudden acceleration of vehicles. Hydrogen is considered to be major source of fuel in the future. Where will we get the hydrogen? There are two sources for hydrogen. One potential source is fossil fuel. So there goes, we still using fossil fuels. 90% of world supply of hydrogen come from methane. Right now, what we do is the natural gas. We do a steam reforming with steam, heated up with steam, with water, produce hydrogen and carbon dioxide. So that is the process, but it still produces carbon dioxide. that's a no-no. But energy-wise, it also produces carbon monoxide or carbon dioxide, incomplete combustion and complete combustion. So, but these reactions produce carbon dioxide and carbon monoxide. Therefore, as far as bringing down global warming, climate change, this is not a good idea. But reform methanol fuel cell. Hydrogen fuel cells are methanol. You can use it in a fuel cell directly to produce hydrogen directly in the fuel cell, feed into fuel cell. You have natural gas, heated it up with water in the vaporizer, then produce hydrogen and send it to the, but it still produce carbon dioxide here. So that is a drawback of the reform methanol fuel cell technology. Still produce. Direct use of hydrogen is the best. Now, direct use of hydrogen comes from water splitting by electricity, electrolysis. You can have a battery and produce hydrogen and oxygen if you have electricity. So then you can insert them into fuel cell. And produce use in a car. Now, apart from the battery, you can also use sunlight. There are batteries which absorb photocells, which absorb, not batteries, photocells, which absorb sunlight and produce hydrogen and oxygen. Sunlight could be used to split hydrogen, water into hydrogen and oxygen. Also, batteries could be used. Out of these two, the second choice seems much promising, directly splitting water to get hydrogen. So they're still working. It's about 20% efficient of converting sunlight into hydrogen. Hydrogen and oxygen gas produced can be obtained by electrolysis of water using battery power or sunlight. These are the two choices to obtain hydrogen from splitting. Right now, there's not much promise with hydrogen producing by that technology. So electrolysis produces no carbon monoxide or carbon dioxide, but it also requires a lot of energy. So electrochemical source or sunlight photoemic is only 14%. I said 20. The bottom one is only 14%. That's not high enough efficiency. But we have plenty of sunlight. If we can produce solar arrays where we collect hydrogen from splitting water into hydrogen and oxygen, that's a good thing. We need oxygen also. So now there's another problem with fuel cells using hydrogen. How do we safely store hydrogen gas in a car? Gaseous hydrogen requires different system for storage and transport from that using liquid gasoline. As a gas, hydrogen has very low density, take up a lot of space. For example, sea level and room temperature, hydrogen volume about 11 liters. The gasoline contains much mass per kilogram for 11 liters. So therefore, the material density is very low for hydrogen. Pressurized gas tanks are very dangerous. We always think about Hindenburg accident because they use a balloon with hydrogen. Hydrogen can explode. But it is promising to use the compounds such as metal hydride, for example, lithium hydride, that can reversibly store significant amount of hydrogen per unit mass. They're trying to find storage material, chemicals that store hydrogen and make it readily available for use in fuel cells. So metal storage in metal hydride is a thing that going right now, research undergoing right now. So these could be included in storage tanks. So release hydrogen as required. So they can store more hydrogen than pressurized tank. The fastest way to store hydrogen gas is to structure some compounds such as metal hydride. Now we're going to talk about little bit about recycling battery. What can you do to keep metals used in batteries from being lost to landfill? So most of the time we just throw it out in the garbage can. The answer, battery depends on the battery type. Search the internet to answer the following. So some batteries contain expensive metals. Which type of batteries are commonly recycled? Rechargeable, secondary, or non-rechargeable? Rechargeable is the most commonly recycled battery. Rechargeable are the recycles more. Why is recycling can be more critical than recycling alkaline? Alkaline earth contain materials which are not difficult to find, but nickel cadmium is limited resources, so we have to start thinking about recycling as we use more nickel cadmium batteries. List some of reason why household battery recycling providers have not been as effective as those for recycling car batteries. Car batteries are more recyclable because we get a $10 back after we take the battery. They are recycled. The car batteries are used as raw materials for producing new batteries. Sustainability of energy storage diversity. Could metals become extinct? As we use, yes. There's a periodic table that describes the availability of different metals. If you look at this one, what is in red are already endangered. What is in orange is required recycling, increase. Okay, let me rise in threat from increased use of orange. Serious threat in next 100 years. Limited availability. Future risks to apply. So green ones are okay. So if you look at battery manufacturing, lithium is endangered. So limited supply. Therefore, we cannot depend on lithium-ion batteries because it's going to be gone over a period of time. Tesla would be okay since they have access to mines and raw materials. But as we deplete more, it would be a problem. There are other batteries in development to replace lithium-ion batteries. In the industrial scale, to produce a working battery takes years to perfect. Therefore, once it's perfected, it's kept using in mass production. So to compete with that, another system has to be developed. It takes time. So we need to start working with more available metallic material to produce ions, produce batteries. Is it really possible for metal to become extinct? Yes. Which of the highlighted elements are currently in demand for energy storage devices, fuel and supercapacitors? Batteries currently in high demands in nickel, fuel cells, some platinum material. Platinum is expensive. Fuel cells has a long way to go. Supercapacitors also, I'm not sure about what exactly fuel cells supercapacitor used, but there it could be found out, search in the web. Are there any non-highlight elements that are currently used or tested for use in energy storage application? These are all web searches that you can find out. Now let's talk about, are electric vehicles really sustainable? Electric vehicles have advantage of fewer direct greenhouse gas emission from their use relatively fossil fuel cars. However, greenhouse gases are emitted during their production and end-of-life recycling effort. So we have to think about recycling and production footprint of these materials, making batteries. In addition to the emission from power plant, in supplying electric grid power needed to recharge batteries in plug-in electric vehicle and electrical vehicles, plug-in hybrid electrical vehicles and electrical vehicles. So we need to consider long-term sustainability of these battery-powered vehicles. As a group, use a variety of sources to answer the following question and determine whether gasoline-powered or electric are more sustainable over their lifetime of use. What is the total global electric demand of electrical vehicles? Now, they're going to take up some of the grid electricity to charge the batteries. So therefore, that's going to be considered important factor in deciding how we produce electricity to provide outlet for different electrical vehicles. What is the current power generation mix in US, including biomass, renewable, hydroelectric, nuclear power, fossil fuels? How does this energy distribution offer other parts of how is the project to change over the next 10 years? So these are the things that if you want to really find out, you have to go to web page, the web browser, and do the research on that. So how do the global greenhouse gas and other pollutant compare between gasoline power? Consider use of end of life. Total life cycle has to be taken into account of the electrical vehicle battery production and recycling. Now I have finished chapter 7. So I gave you an overview about total storage devices in cars, in devices, electronic devices, computers, laptops, how we use battery power, and little bit of everything. I will see you on